So let us start the second part of the lecture. But I realize that I don't need to go back to this long remark. That is the difference between Cauchy principal value and this integral, which we faced here, and you saw the differences. Yes. But this is the simplest possible example to differentiate between the Cauchy principal value and the real definition of that one. So you can read it, of course, yourself. Before those exercises, I try to give you the simplest possible example to see what is the difference between these two concepts. So forget about, in your course, you don't have anything about the Cauchy principal value. So what is given to you is just a calculation of the integral based on the definition. Okay, now we go to the second type of integrals, improper integrals. So this one, we want to relax the first condition. So you remember, in the Riemann integral we discussed, the function was bounded and the interval was closed and bounded. In the first improper integral, in this first type, we relaxed that it is not necessarily the case that the interval is bounded. But here what happens if the function is unbounded or it has some singularity within the interval? Okay? So this means, for example, I would say that if I have a function, yes, and then I am working on this interval from A to B, okay, so the function f is continuous everywhere, probably it behaves badly at one of these endpoints. It has some singularity for being unbounded in this endpoint, at this endpoint, at that endpoint, or somewhere in the middle. If this happens, that is called a type 2 improper integral. Yes? So for example, if I just want to give you immediately something, so if I write this, I am in trouble. Yes? Because this function 1 over x is my function. The interval is from 0 to 1. And this function behaves badly at 0. Okay? Or in other words, in this case, when I get closer and closer to 0, this becomes unbounded. Yes? Or might be I have troubles with both. I don't know, for example, so you can have, for example, this integral 1 over x squared minus 1 dx from minus 1 to 1. Then I have trouble in minus 1, and I also have trouble in 1. So all this, but this is a little bit harder to detect. The type 1 are easy because you see by your eyes infinity somewhere on the interval. Yes? But when I give you this type of integrals, you might think that, okay, let us do it the normal way. Okay? But you have to sharpen your sight to see that, no, this is an improper integral because I have problems for this function at this point. Do you see that? Understandable for everyone? Yes, please?
Would you be able to do it normally, but then instead of substituting 1 and 0...
No, it means you shouldn't do that. If it happens, it is a coincidence.
Okay.
If it happens to be true, the way you do it, because if the function, these singularities somehow removed in the middle of the calculation, you come up with the correct answer. But that is a coincidence, so you have to follow the rules. Okay? We have to have a new definition, because our old definition, the ingredients of our old definition was bounded function, bounded closed interval. So it means that we are extending the integration theory to contain new integrals. You cannot do what you did before, because that is not what you had before. Yes? Because I'm just writing it with the same symbols, it means that that is not the same mathematical creature that we just discussed before. Because for having that before, I need to have f bounded, I need to have a closed bounded interval. Yes? So this means that this is an extension to the theory of integration to include new integrals. Okay, so what I want to tell again here, that I don't have any problems with my interval. These are just normal intervals. But singularity occurs for my function either here or there or somewhere in the middle. These are called type 2 intervals. And you have to be careful about that. And when you receive a question in the exam and you see it's very, very simple, always think that it should be a type 2 improper integral. Yes. So, now we want to discuss about that. Okay, so let us consider the case that I have this problem. So I have integral of f of x dx from A to B, but my problem lies here. So this function behaves badly here. If the function behaves badly here, it is unbounded or it has a singularity there, it's not defined there. How do you define it? You say that, okay, exactly like before, more or less the idea is the same. So instead of going from A to B, you go from another number C to B, but C is where? Is a number chosen within this interval. Yes, so you choose a number within this interval, so you intentionally avoid this A. You choose one number there, and then you calculate your integral. So I am assuming that my function is continuous everywhere except possibly at A itself. So when I remove that A and I choose C somewhere here, it means that, so you see this interval, this is A, this is B, C is chosen somewhere here. And then definitely from C to B, my function remains continuous. And if it is continuous, it is integrable. So this function exists, this integral exists if C is there. But now I want to have a definition for that. Do you have any intuition? Based on what you learned before about sending limits and calculating limits, what do you think I will do here? What is a reasonable definition? By the way, at the end it's a definition, mathematicians define it for you. But there is some logic behind that. You see that I want to take the limit, can you tell me how?
C approaches A from
C approaches to A, yes, but from the right hand side. So this is what you write. This is the definition. Again, as before, let me ask you one question. This integral is a number, but this number depends on this C. So it's a function of C. You calculate that function of C, and you take the limit of that function of C when C approaches to a number from the right. So you reduce your problem to a limit problem. In principle, you should be able to do it. Yes? So let me just immediately ask your opinion about the other scenario. So what happens if I have integral from A to B, f of x dx, but the trouble here, so if you don't mind, let me just quickly go. So this was the trouble some number. So if the trouble is here, what do you think I will do? This time I will write integral, again from A to C, fx dx, but this time I take the limit but send C to B, this time from below. Okay? So I'm just telling you that so that if you forget somehow, these are definitions, so you have to have them in memory, but they are reasonable, so you can cook it up if you forget something. Any questions? So this circle here means that my function is probably singular at this point, and this means that my function is probably singular at this point. Is that clear? So technically speaking, this is not something new, but instead of working with limits at infinity, you will work with limits at numbers. Yes? So for example, you can use Hopital's rule and everything you have learned before. So if you don't mind, let me immediately start doing these examples. Evaluate again each of the following integrals or show that it diverges. The terminologies are exactly identical. So let us start with very, very simple example. Integral from 0 to 1, 1 over x dx. Okay, so this is given to you and you are supposed to, of course, immediately when you see the question, you understand this is related to improper integrals. So, this is my function. I have only problem here because this function is not defined for 0. It is unbounded close to 0. So what do you think I will do? I will use a definition. So I will introduce an integral which depends on C, exactly as before. But this, can you tell me what this integral should be?
C to 1.
C to 1. Yes. So let me put semicolon here. I define it for you like this. And then I focus on calculating IC with the knowledge that I have for integration. So IC becomes, this is a very famous integral. So it becomes ln of absolute value of x. I run it from C to 1. So this becomes ln of 1, 0 minus ln of C. So I just want to emphasize, do I need absolute value here? No, because I choose C to from this interval, and that interval is from 0 to 1. So C is automatically positive. So I don't. Of course, it doesn't matter here, but let me just be careful. Yeah, okay, I've already done that. So I don't need absolute value. So this becomes minus ln of C. Do you agree with me? Yes? Okay, now what should I do? I go to the definition. So I take the limit of IC and I send C to where? To the lower number of my integral 0, but from above. So it means that I send it to 0 from above. So this means that I am going to calculate minus ln of C when C goes to 0 from above. So what's the answer?
Plus infinity.
Plus infinity, because this one becomes negative, negative is plus infinity. But you have to write the answer, so hence the integral diverges. Yes? So these are good problems. The hard ones are the ones that you don't know how to calculate the integral and you want to use another theorem, which is comparison theorem. That would be a little bit problematic. Probably we will start this on the next lesson, but let us see how it goes. Let us go to the next example. Integral from 1 to 2 dx over the third root of, what is that? X minus 2. So if you see this integral, even if you don't see the title of the question, you should understand that you are facing an improper integral of the second type. Why? Because I have a problem for my function at this upper limit. If I put 2, 2 is a singularity for this function. Okay, so this means that you know what to do. First, you define a function of C. In which way? This is not problematic, so you keep it. This is problematic when you replace it with C, and then copy and paste everything else. And then focus your energy, use your toolbox to calculate this integral for the first part of this lesson. So how should I do that if I want to calculate this integral? Do you have any proposal? You should be good in these calculations now. Don't doubt. You have to do something. Yes?
3 over 2 cube root x minus 2 squared.
Okay. You just gave me the answer.
Yeah.
No, but if you don't know the answer, we want to find the answer. What is the method? Do substitution. So, which one you want to take u? X minus 2. Okay? But let me tell you another trick. X minus 2 is good. But let me, even though it seems strange, but I want to take the whole thing u. Okay, so this is good. I want you to learn this one. I didn't talk about that because I didn't want to confuse you back then. The natural u is to take x minus 2 to be u. Why? Because the derivative of x minus 2 is 1, and 1 is of course sitting here. That is the most natural one. But it is not the most efficient one. If I want to do it, instead of taking that one to be u, I will take the whole third root to be u. But I deviate a little bit from my own strategy. So I told you immediately take the u, but this time I wired myself and said, no, don't do it immediately. Raise it to power 3 and then take the u. Okay, so what I'm saying is that then it becomes u third, it becomes x minus 2, and then I differentiate. When I differentiate, the right hand side, the derivative is 1 times dx, but the left hand side usually always is du, but this time it becomes 3u squared du. Okay, this kind of, whenever you are working with these, some root of something, if you think the method of substitution is suitable, instead of taking the expression below u, it is more efficient to take this one u because it will help you to avoid fraction powers. That's it. It's not a very big miracle, but it is better than working with fraction powers. Okay, so now let us see what happens. One more thing I have to do, because that is a definite integral, I need to know where u goes now. So I know that x goes from 1 to c. This implies that what? U goes from, I put 1 here, so 1 minus 2 minus 1, the third root of minus 1 is minus 1. And I put c here, so it becomes the third root of c minus 2. Yes? Okay, then what happens? I put everything back. So I of c is equal to the integral. Instead of 1, I put minus 1. And instead of c, I put the third root of c minus 2. Instead of dx, I put 3u squared du. And instead of the whole denominator, I just put u. If you don't like it, do it as before. It doesn't matter. Take this one here. Okay, so this one u and one of those u's are cancelled. So 3 goes out, u is left. So it becomes 3 over 2 u squared.
U.
No, u goes, no, this is the integral. I'm doing it
you're
2 steps.
Yeah.
And then it goes from minus 1 to this number. Yes? And then you substitute. So this means that I of c is equal to 3 over 2. I put this expression here, so it becomes the third root of c minus 2 to power 2. And I put minus 1 here, so it becomes minus 1. If I put minus 1, it becomes plus 1, but I'm subtracting. So that's my IC. And then I take the limit. You remember? I want to calculate this integral. My problem was a 2, so I replaced 2 with c. So now I calculate the limit of this when c goes to 2, but from below. So this becomes the limit of 3 over 2, the third root of c minus 2 to power 2 minus 1. C goes to 2 from the left. So what the answer is? It's minus so yes, if I put 2, it's gone, so it's minus 3 over 2. Yes, you're right. By the way, is negative acceptable? Is understandable? It should be negative. I was doubtful a little bit about that. Yes, because on this interval from 1 to 2, x minus 2 is negative, and the third root of a negative number is also negative. So if it goes to be a number, that number should be negative. So at the end you have to write this, so let me just not write it. You would write, yes, the original integral converges to minus 3 over 2. Is that right? Okay. So now let us do the next one. So integral from 0 to 1, ln of x dx. This is a very innocent integral, but I hope that you can see this is also problematic of second type. Yes? Why? Do I have any problems with the upper limit? No. ln of 1 is 0. But I have a problem with 0. ln of 0 actually goes without bound. Yes, it is undefined. It's a singularity. It's undefined point for ln of x. So it's already telling me that's a second type improper integral. So what do? Again, you introduce a function. Your problem is here. So you would write it from c to 1, ln of x dx. And then you have to look into your toolbox to see how can I calculate this integral for the first part of this lesson. Do you have any idea? Anyone else? Yes?
By parts.
Integration by parts. And if you don't mind, let me do it my own way, okay? So I will take this u, and I will take this dv. And I would write the formula integral of u dv is equal to uv minus integral of v du. But this is the definite version. So the definite version will be this. Okay? Okay, so do you remember in this formula, if I take this u and take this dv, then my integral will be u dv, which is good. On the right hand side, I need u, I have it. I need v, I don't have it, so I will find it. And I also need du, I don't have it, I have to find it. So what I will do, I would say that u is ln of x according to me. And then I take du, this becomes 1 over x dx. And then dv is equal to dx. So So what is v? One possible v, which is enough for me, is just x. Yes, and then I put everything back into my formula. So I of c is equal to u times v. This is your u, this is your v, multiply them. But this is a definite one, use the definite version of it. It goes from c to 1. Minus the other way around, minus integral from c to 1, but v du. This is your v, this is your du, multiply them. Yes? Okay, so here I have to replace x with 1, I get 0 because ln of 1 is 0, minus, I put c. And this one and that one are gone, integral of dx is just x, and I have to go from c to 1. Yes, so what happens? Am I right? So this one is integral from c to 1, this is gone. So this becomes x from c to 1, which is 1 minus c. Yes? But if you don't mind, let me open it up. So this becomes c minus 1 minus c ln of c. This is my IC, but what I have to do, I have to calculate the limit of I of c when c goes to where? To the problematic one from above, 0 from right. Okay, so this becomes the limit of this one is 0. This is not a problem, but what type of limit is this? It is 0 times infinity. Why? Because if c goes to 0, this is 0, ln of infinitesimal is minus infinity. So this is 0 times infinity. So I have to use Hobbital's rule, but this is one of those cases that you have to invert it 2 times. So let me calculate this one first. So I will calculate the limit of c ln of c. c goes to 0 from the right. So do you remember? I want to do something to use Hobbital's rule. Hobbital's rule does not directly is applicable to 0 times infinity unless you change it. So first of all, do you agree what I have written is valid?
Yes.
Yes, because ln of c over 1 over c is the same thing. But what is the benefit here? Now if c goes to infinity, the numerator is minus infinity, the denominator is plus infinity, so it is infinity over infinity, and second Hobbital's rule will apply. Yes, so it becomes, but the differentiation of course is with respect to your variable. Okay, so if I differentiate this, it becomes minus 1 over c squared. If I differentiate this, it becomes 1 over c. And if I simplify things, it goes to the numerator, so it becomes limit of minus c, c goes to 0, and that is 0. So, the limit of IC, so therefore, what happens for the limit of I of c? What is the limit? The limit of this part is 0, the limit of this part is minus 1, and the limit of this part I calculated to be 0. So it is 0 minus 1 minus 0, so it is minus 1. Is the negative answer reasonable? Yes? Because when I am between 0 and 1, ln of a number less than 1 is always negative. So if the integral is going to exist, it should be better to be a negative number. Any questions? Okay. So let us solve the next one as well, and then probably we'll skip something to see what is left for us. Okay. So for example, the next one seems a little bit hard, but I don't think it is. So it is integral from 0 to pi over 2. And then you have 1 minus sine x to be what? To which power is that? 2 over 3. And then I have cosine x dx. Yes? Again, when I give you this integral, you have to be very careful. If it's just written like this, evaluate or assess the following integral, it is hard to see that this is type 2. So you have to make your brain conditional to check if it is a type 2 integral. Is it? Yes, because at the top one, pi over 2, I have a singularity of my function. Sine of pi over 2 is 1, 1 minus 1 is 0, I am in trouble. Yes, so I have to use the definition. So it means that I immediately introduce integral which depends on c. The problematic is this one. I keep the one which is not problematic, and I will replace this problematic one with a c or any variable that you like, but not x, of course. And then I will copy and paste everything, okay? Okay. So what kind of technique you have in your toolbox to do this? With u substitution, yes. Which one is good to take u? For example, you can take sine x to be u, but then you have to do another one. But if you take the whole combination, u is a better one. Why it is a good one? Because if I differentiate sine, it becomes cosine, and cosine appears as a factor there. So it's already an indication. But again, if you are comfortable with what I did before, if you are not comfortable, take 1 minus sine x to be u and calculate and work with fraction powers. But if you want to do, I will prefer to take this one u. I'm not saying that this is the best one. I prefer not to work with fractions when it comes to the integrals. That's just my taste, okay? But I want you also see this technique. So if I take this one u, the most natural one was this one. And if you do the most natural one, what do you do? Immediately you calculate du and continue. But if you do this one, by this trick I am getting rid of the fraction power. Don't take du immediately. Raise it to power that you get rid of this fraction. Which power is suitable here? U to the power of 3. And then it becomes 1 minus sine x. I hope that I'm not confusing you. I am adding one small tool to your toolbox with the substitution method. Okay? But then you take the derivative differentials from both sides. This time this is 3u squared du, and the right hand side becomes minus cosine x dx. Okay? And then x goes from 0 to c. This implies that u goes from where to where? If x is 0, I get 1, so u becomes 1. This one, of course, becomes problematic. There is no way we can escape everything. But I myself prefer to get rid of fractions in the integrand. So if I put c here, it becomes 1 minus sine c to power 1/3. And if you don't mind, let me just write it the third root. And then I put everything back. So I of c becomes equal to the integral. Instead of going from 0 to c, I will go from 1 to this a little bit complicated one. But in the denominator, what should I write? Can you help me? This is u, but the denominator has also an extra power of 2. So it is not u, but it is u squared. So it is u squared, and then you see how good is this. Because now, cosine x dx is negative of 3u squared du. Yes? And then what happens, this u squared is completely gone. So your integrand is extremely simple now, even though the price you have paid is to have a little bit more complication in the upper limit. Okay, that's up to you which one you prefer. Okay, so this minus 3 goes out, integral of du is u, so it is just simply minus 3u, but I have to run it from this number to that number. So this means that I of c that I was looking for, if I put these numbers and subtract them, so if I put 1 there, and if you don't mind, let me factor a 3 out, so it becomes this one. I replaced u with these numbers and subtract them. And I write them in a better order. I always prefer to start with positive one. I'm still optimistic to humanity, you know. So I start with positive things, yes. Let us see how it goes. So the limit of I of c, I have to send c to where? Where? The problematic one. The problematic one was pi over 2, so I have to send it to pi over 2, but from below. So this becomes the limit of 3 times 1 minus the third root of 1 minus sine c, and then c goes to pi over 2 from the left. I'm sorry. And then this is simple. What is the answer? And what's the answer?
3.
3, yes? Because if I put pi over 2, sine of pi over 2 is 1, 1 minus 1 is 0. So this is just simply
3.
Yes? So the answer is 3. Is that okay? So it means that we are just adding one kind of limit process to both of them, okay? But you have to be a little bit careful. But now there are more subtleties coming in. I will skip question number 611. It's a very simple one. If we have time, of course, we can do it again. But let me read this one for you. This remark is important. While improper integrals of type 1 are always easily recognized because of the infinite limits of the integration, improper integrals of type 2 can be somewhat harder to spot. You should be alert for singularities of integrands, especially points where they have vertical asymptotes. I mean, they go to, of course, if we have time, we'll also cover asymptotes. By the way, I have put some videos from my high school teaching. That is even more than what you need in this course. So please, if you don't have time, watch those videos, okay? That's exactly what you need to cover for asymptotes here.
Did you have a favorite student?
Yes, I had a lot of favorite students back there in high school. Yeah. So I had them for 3 years, so they get used to my method. So I was teaching them from the first grade. They were resisting first, but then after 1 month, they started actually liking it, yes. Because they realized that they are understanding something. Okay, so it may be necessary to partition an improper integral, that's important, into several subintegrals if it is improper at both endpoints or at points inside the interval of integration. For example, let me just emphasize it here on the board. Might be you'll learn better here. So, for example, I don't know, this is an example I picked from the text of your book. And we are not talking about if this integral is doable or not, but I just want to tell you what do I mean by this. So if you have this integral as square root of, this one. This integral, this is what I'm saying, that I don't have any idea in my toolbox to calculate this integral. Okay? So that will be the topic of probably in the beginning of tomorrow's lesson. That even though we cannot calculate the integral, is there any way that I understand this integral converges or diverges? Even if I cannot calculate the exact value. But that's also important. Yes? So sometimes, for example, I remember in physics, for example, you want to calculate something, and then you calculate integral over an energy spectrum. It's very important for physicists to see that if this integral converges or diverges. Because if it diverges, it is not describing any physics of reality of the universe, yes? So, and the integral is too complicated to calculate it exactly. So it is important, this is an important real question, that even if we cannot calculate the value of integral, if you want to see our physics theory is a correct one, you want to really know that this integral converges or diverges at the end. Because if it diverges, we are in trouble as a physicist, yes? Something like this. So this will be the topic, probably I will not be able to start it. But this one, if you want to see it, can you see that is an improper integral first of all or not? Do I have any problems with minus 1? Do I have any problems with minus 1?
No.
No. Because this becomes 2? No. And this is also 0. So no problems. But do I have problems in the upper bound?
Yes.
Yes. What is the problem in the upper bound? Not the numerator, the denominator vanishes. But I also have another problem in the middle of the way. Yes, and that is 0. Okay? Because 0 is good for the denominator, but it's bad for the numerator. It blows up around 0. So, but 0 is hidden. This means that you have to break up your integral. And there are some theories. How can I break them? Is it dependent to the number I'm breaking? Something around those lines that I was talking about the first time. I tried to motivate you. I didn't prove it. I have given you some examples because that was very simple to follow. So, it doesn't matter how you break it. If it is convergent, no matter how you break it, it will converge to the same value. Okay, so for example, if I want to investigate this integral, because 0 is also problematic of the second type, so I will probably break it from minus 1 to what? to 0, for example, yes, I will consider this one. In this way, I have problem only at upper one, yes, because of the numerator. Then what do? I go from 0, but I shouldn't go to 1. Because if I go from 0 to 1, I have problems both at 0 and at 1. Do you agree? So I break it from 0 to some number in the middle. Probably the first choice comes to mind is 1/2. And then I go from 1/2 to 1. So this means that if this integral is given and I want to investigate that, I will investigate 3 integrals so that I have only one problem with one limit at a time. Yes, here I have only one problem, that is the upper limit. Here I have only one problem, that is the lower limit. And here I have only one problem, that's again upper limit. Okay? And then, which one you prefer you will start with. If you are lucky and one of them diverges, the process stops and you conclude that the whole integral diverges. If you are not lucky, or I don't know, of course, it depends how you look at it, yes? So, but this one, if you work it out and it is convergent, you have to go to the second one. If it works out and it's convergent, you go to the third one. If all of them converge, then it means that the integral converges and you add up the values. But in principle, you have to break your integral to different integrals that you have one problem at a time. Okay? Otherwise, you have to algebraically actually take different limits, but that is not plausible. Understandable? Okay. So, for example, let us do one of these problems. Might be that is good. I don't know which one we have to do, so the battery is also dying. Hopefully, we will be able to manage that. So let us do example 6.13. Let us do the first one, because that's also something I haven't talked about. So you know you have to have a lot of things in your toolbox, and your calculus is a little bit extended course. So integral from 0 to 1 dx over square root of x times 1 minus x. Yes, I hope that this battery does not die. So if you don't mind, let me take this off. And then I put my charger here. Yes, because we don't need that anymore. So, do you see that this is one of the integrals that I discussed for you, yes? Because I have an integral. It seems an innocent integral, but it is problematic, yes? So, because I have, by the way, I have 2 problems here. One at 0, this makes this one 0, and one at... So it means that I have type 2 integral, but both bounds are problematic. So what should I do according to what we learned? A split, yes? A split means that pick any number. Of course, it should be a theorem, that splitting point does not matter at the end. Okay, but these theorems are not discussed here in this course, but trust me on that. So what I will consider, which integrals you want to consider, tell me. You have 0 problem, you have 1 is your problem. You want to break it into 2 integrals, 1 problem at a time.
0
To half. Half is the most natural one, but if you want, you can choose 1/3, okay? So anyway, so this x, and then you have square root of x, 1 minus x. And then I have another one from 1 over 2 to 1 dx square root of x 1 minus x. Yes, so in the exam you should mention that I have 2 problems, so I investigate 2 integrals instead. One this one and that one. Okay, so what do you think we should do now? By the way, when you break the integral into 2 parts, because the integrands are the same, don't try to repeat the problem 2 times, because most of it is the same. You want to find a primitive function. So might be, I'm just talking intuitively, so that might be, let us work it out, only one integral without limits, and then use that primitive function for this case and that case. But if you want, you can do it separately. Yes, please.
If we know that this particular function is symmetrical around 1/2, can we just solve one?
Exactly, but you have to defend yourself. But when I'm teaching here, I don't want to use this because it will confuse people. Yes?
I'm saying if if we know that it's symmetrical, that
Yes.
we can just take one of them and then times it by 2.
Yes, but you have to be careful you are following the definition.
Yeah, right.
Yes? Because I don't know, you were absent for the first part. There is a difference between Cauchy principle for the first types. So for example, this integral, so because this is odd, your guess is that might be the answer is 0, but the answer turns out to be divergent. Yes? So you have to be careful about these things. But if you can take care of everything in detail, so yes, that's okay. So here, if I want to do it, do you know how to do it even? How should I do this? We haven't talked about this systematically, there is no time for it. But in principle, you have the tools in your toolbox to do it. So what type of function you are facing here? X minus x squared. X minus x squared is a polynomial of degree 2 with the square root on it. Which function, which integrand was close to this? We didn't have this. We didn't discuss about these integrals systematically. But in principle, this is doable. This is a square root of a second degree polynomial. Do you remember any formula that you had a square root of a second degree polynomial somewhere in your toolbox?
Arcsine.
Arcsine. And what was that? It was integral of dx square root of a squared minus x squared. The answer to this integral was arcsine of x over a. So this is the closest formula you learned to this integral. But this is of course not that one, because this becomes dx, the square root of, if I multiply that, it becomes x minus x squared. The problem here is that x squared is good, but I cannot give the role of a squared to x, because a squared in this problem is constant, but here is x. So it means that I have to do some adjustments, and that is a little bit high school algebra. Yes? I can write it in this way. I want to make the square complete, yes? So it becomes complete the square. So it becomes x minus a half to the power of 2. So the first, and then I put a minus sign here to take care of this. The first one is squared, x squared minus sign. I already took care of that. 2 times the first one times the second one is minus x, another minus plus x. But unfortunately, when I raise it to power 2, it gives me 1 over 4. It's a minus sign, so I have to add 1 over 4 here as well. Do you agree now? So what, if you don't believe, open it up, and then you'll get this one. So I am doing the complete square method, what you learned in high school, so it's very important. Your poor teachers actually cried, learn these things, these are important, you didn't care that time. Okay, I hope that you care this time, okay? So 1 over 4 minus this one. So what is the next step? It is similar to this one, but that is not identical. But hopefully at this level you should be able to tell me what to do immediately. Substitution. Because if you take x minus 1 over 2 u, so dx becomes du, there is no difference actually. And then what do I have? This integral becomes du divided by square root of, instead of 1 over 4, I write 1 over 2 to power 2 minus u squared, because I want to make it as similar as possible to this one. But this is a famous one. So this becomes arcsine of what? U divided by 1 over 2, which is 2u. And if you want, you can put your variable back. Arcsine of 2 times u, which is 2x minus 1. Yes? This is better because you know that in both cases I need this integral. So why should I do it 2 times? Okay, so if you don't mind, this one is problematic, so I will define I of c to be integral from c to 1/2 dx over square root of x 1 minus x. And then I define another one, j of c. If you don't mind, let me choose a different letter. It doesn't matter. D. The problematic one is this one above. Yes? But none of them I am in trouble because I already found my primitive function. So this becomes what? This becomes arc sine of 2x minus 1, but I have to run it from c to 1/2. So what is the answer? If I put 1/2 there, arc sine of 0 is 0, so it becomes minus arc sine of 2c minus 1. Okay, but now I have to take the limit of IC when C goes to 0 from the right hand side. So what's the answer? I put 0 here. Arc sine of -1 is minus pi over 2. There's a minus sign here, so this becomes nothing except pi over 2. And this one, is this D a good sign? It's strange, yes? So let me call it alpha, whatever you want. Okay, so then what happens? This becomes arc sine of 2x minus 1, and then I go from 1/2 to alpha. So this becomes arc sine 2 alpha. Because if I put 1/2 again, I am. But then I have to take the limit of j alpha, and I send alpha to what? To the problematic one. What was the problematic one here? What was that? It was 1 here. Yes. Alpha 1 from the left. Am I right or not? No, this is not correct. You know why? Because when I put alpha here, this is 2 alpha minus 1. I was in trouble, I realized. Am I right now? Yes. And if I put alpha 1, this becomes arc sine of 1, which is pi over 2. Yes? So what can you conclude at the very end about the original integral? Does this converge or diverge? Because both of them converge. This is also convergent, and it converges to the sum of these values. Yes? So this means that the original integral converges to what? To what was the first one? Pi over 2. What is the second one? Pi over 2 is equal to pi. So that's the answer. Yeah, but the hard part of this lesson, I have written all the questions in the workshop, but of course we will also have, today you have seminar, yes? Yes. Okay, so for the next time, we will completely cover this one. And the hard part of it is still left. And that is the case that we cannot calculate the integrals, but as I told you, for example, in physics, we want to see if this integral converges or diverges at the end, even we don't know the exact answer. Any questions? Thank you very much. See you tomorrow.